Hello everyone, my name is Pietro Barbieri and the title of our work is Sound Regular Corecursion in CoFJ. We will discuss about corecursive featherweight Java and two semantics we have proposed for it. Then we will present the soundness result which relates these two semantics. CoFJ is an extension of featherweight Java which allows the manipulation of non-well-founded data structures. We have co-definitions, which are alternative method definitions used in a special way. We propose an abstract semantics allowing infinite objects and based on flexible coinduction, as well as an operational one that manipulates regular object and based on regular corecursion. This is the CoFJ syntax, and as you can see, the only difference with respect to the standard FJ1 is the introduction of this optional co-definition specified by the keyword corec. Moreover, the production for values is interpreted coinductively, since we want to allow for infinite object. This is an example of some classes defining lists in CoFJ. We have a method allPos that returns true if each and every element of a given list is a positive number. We specified a co-definition for this method that simply states true. Indeed, the co-definition is used to specify the behavior of the method in presence of infinite lists. In CoFJ we can build possibly infinite objects. For example, this is the list of natural numbers defined by new not empty list 1, 2, 3, etc. abbreviated with this notation. Moreover, we can also have cyclic lists, and this is an example. We have a new not empty list 1, 2, 1, 2, etc. abbreviated by 1, 2, omega. Ideally, we would like method allPos to return true when called on these two infinite lists. We present now CoFJ abstract semantics, which is defined by rules and co-rules. These are the rules and they are all quite standard. We have the field access, the constructor new, and the method invocation. For this last rule we have that the receiver and the arguments are evaluated first. Then we use this auxiliary function mBody to retrieve the body of the method e. Then e is evaluated and the result v is returned. We have a rule for values also. Then we have a co-rule. The co-rule behaves differently from the standard invocation. In fact, we have, after having evaluated the receiver and the arguments, we use this auxiliary function co-mBody to retrieve the co-definition, and the co-definition is evaluated instead of the standard method body. Then the result v is returned. In these semantics, rules are interpreted coinductively and infinite proof trees are allowed. However, each node in the infinite proof tree should have a finite proof tree, using also co-rules. In this way, spurious results are filtered out, and we achieve the desired semantics. Let's see an example. We have this infinite tree, starting from the call 1 to omega dot allPos. We check if 1 is positive, and then we call the method on the tail. The tail of 1 to omega is to 1 omega. Again, we check if 2 is positive, and we call the method on the tail. The tail of 2, 1 omega is 1, 2 omega. We can clearly see that this tree is going up to infinity. However, the result true is correct. Since we are using the purely coinductive semantics, we can also derive this result, which is obviously wrong, since we are stating that this method call returns false. In our semantics, thanks to the use of co-rules, we have that only the first tree, which is the correct one, has a finite proof tree using corules, using one corule in this example. Indeed, method allPos has the codefinition true, and the finite proof tree can be built only for the correct infinite proof tree. Thus, the wrong one is filtered out and we only get true as a result. For what concerns the operational semantics, we must have a finite representation of regular objects. To do that, we use capsules. Capsules are couples in which E is an expression and sigma is a finite mapping from variables into expressions. For example, the list 1, 2, omega is represented by the capsule x followed by x associated with new, not empty list, 1, 2, and again x, and we built the cyclic list. However, we cannot represent the list of natural numbers since it is a non-regular object. In the semantics, we use regular recursion, that is, we keep track of already considered calls and we avoid non-termination. Moreover, we added flexibility by using the codefinition. More in particular, the codefinition is specified by the user, and the user can tune the behavior of the function in presence of a cycle. This is the same example as before, but in the operational semantics. Let's see what happens. We have 1 to omega.allPos. We check if 1 is positive. Okay, we call the method on the tail. We get 2, 1 omega. We check if 2 is positive. We call the method on the tail. The tail of 2, 1 omega is 1, 2 omega. Now we have reached the same call as the starting one, so the semantics is keeping track of this fact, and instead of evaluating again the method body, the codefinition is evaluated instead. The codefinition for allPos is true, and then true is simply returned. We have a check-in step in which the body of the method is evaluated once more, assuming the first result, in this case true, as the correct one for the cyclic call. Then, after the second evaluation, true must be returned again. In this way, we are sure that this result is the correct one for this method invocation. The judgment of the semantics is this one, and we have a capsule to be evaluated, E sigma. Then we have a call trace tau, which is an injective map from calls to variables. Tau is used to perform cycle detection. That is, in tau we store already considered method calls. Calls in the environment can also have a tag ck used in the check-in step, and we will see this later on. Lastly, we have the result of the evaluation is the capsule V sigma prime. V is a value. These are the first rule of the operational semantics. We have the rule for values, and we have the field access, in which we note that in order to get to the object, we must unfold the capsule with this auxiliary function in order to retrieve the first constructor. Then we can return the desired field vi. This is the constructor new, which is defined in the customary manner. We now have 4 rules for what concerns method invocation. I will not go into many details due to lack of time, but this is the most important one, invoke check. We start from a method call. We evaluate the receiver and the arguments. Then we know that the call is found for the first time, since the call C is not contained in the environment tau. Then we retrieve the body of the method with this auxiliary function and body. The body is E and is evaluated for the first time. In this evaluation, we update the environment tau by adding the call C to the environment. The call C is the one which we considered, associated with a new variable x. After the evaluation, the capsule result is V sigma prime. After the first evaluation, we note that the variable x is contained in the domain of sigma prime. This means that the codefinition has been used for this call. So we know that the result V must be checked. Then we evaluate once more the body of the method, and the resulting capsule must be bisimilar to the first one. The notion of bisimilarity is a sort of equality between capsules. If this is the case, the result is returned, and we know that the result is the correct one. Rule correct deals with the codefinition, and we start from a method call, clearly, but we know that the call C is contained in the environment tau. So we know that we are dealing with an already considered call. Then we retrieve the codefinition with this auxiliary function, co and body. The codefinition is E prime, and E prime is evaluated instead of the standard method body. Then the result V is returned, and we update the environment sigma prime with the association from x to x to state that we use the codefinition for this call. Rule invoke OK has a starting behavior which is similar to invoke check. Indeed, we have a call found for the first time, since it is not in the environment tau. Then, after the first evaluation, we note that this call, the variable associated with this call, is not present in the domain of sigma prime. This means that the codefinition has not been used for C. Then we know that the result V has been obtained by standard recursion and no check is needed, so we can return the result as is. The last rule is lookup, which is used in the checking step. We start again from a method call, and we note that in the environment tau we have the variable x associated with a tag ck. We know that the codefinition has been applied for C, and the result V needs to be checked. Then, in this rule, we simply return the result stored in tau, and then rule invoke check that we've seen before has to check that this result is the same as the first evaluation of the body. For what concerns the soundness result, our aim is to prove that the operational semantics is sound with respect to the abstract one. This means roughly that a result obtained with the operational semantics can also be obtained with the abstract one. However, values of the two semantics are different. We have possibly infinite objects in the abstract semantics and capsules in the operational semantics. The relation between these two kind of values is that a capsule denotes a set of abstract values, and in order to get these abstract values we need to instantiate variables in V with abstract values in a way consistent with the environment sigma. The proof of soundness is done by using an intermediate semantics, which is an hybrid between the operational and the abstract one. More in particular, in these semantics we use infinite values, like in the abstract semantics, but we rely on cycle detection, as in the operational semantics. Then the soundness proof is in two steps. First, we prove the soundness of the operational semantics with respect to intermediate one. Then, from the intermediate one to the abstract semantics. In this way, we have proved the soundness of the operational semantics with respect to the abstract one. For what concerns the future work, we conjecture that the intermediate semantics might be complete with respect to the regular restriction of the abstract one. Clearly, the abstract semantics is way more powerful than the intermediate one, since we can also have infinite non-regular objects, like the list of natural numbers. But for a regular restriction, we might prove this result. Also, we plan to extend the regular recursion by enriching its expressive power to go beyond the limitation imposed by regular terms. For example, we would like to represent also non-regular objects like the list of natural numbers. And this is all. Thanks for your attention.